All right, assignment number 12. If you watch the lecture video, you might not have any issue implementing this program, basically. In this assignment, you have been asked to complete this program. So this portion given in here, this program, is going to be your main C file. So within this main C file, you're asked to basically implement two assembly functions. One is read character, and the other one is print character. These are going to be your own, basically, function. So what they do, once you call read character, is going to read a string of character from the input, standard input, which is your keyboard. And then it's going to save that in the memory in some location. And what printer character does, print char does, is just take those characters from the memory and print out that on the display. So as simple as this. So the only thing that you need to do is just implement these two functions in assembly. Okay, so this is the program that you're having. So as you can see, here is the main function. So the compiler knows where to start when we compile this code. So I'm going to also explain how we can write the makefile for this program. And then what we need to do, we need to implement this read character function and read character function basically in assembly. So if you have watched the video lecture in there, we explained that when you want to basically define a variable, a pointer that's going to be basically implemented in different files, you need to add the keyword extern. Normally, for function, if you don't add the extern, that's going to be fine. But if you have variable and pointer, you need to actually have the extern keywords at the beginning in order to tell your program, okay, this is a variable that's going to be defined in some other files. For function, it is a default. But in here, I put extern to somehow tell you guys the rules. So this is our main C function. Let's take a look at the read character implementation. So in read character implementation, the first thing that you see is extern character array, right? So this is our pointer. We say extern because this is not defined within the assembly function. Where it defined, actually defined in here. So in our main C file. So we know that this is a pointer. And when we say extern, it means that, okay, this variable has been defined somewhere else. Compiler go and see where it was. But in this file, we are going to use it. This is an external variable. That's the reason we say extern. Now, so we are going to write the code in assembly. So you guys know that the code should go to the section.txt. And we define this read character function as global, meaning that, okay, this is where we define the function. And this function is going to be global, meaning that it's going to be used in some other files. So here's the way that we define the function. You know that for read, basically, we are going to program 4 different registers in our CPU. You guys know this, it's going to be EAX, EBX, ECX, and EBX. So once you program this, then you call the Linux kernel to basically have this system call and ask the system to provide you the I/O devices that you need. And then the system call is going to take a look at the register EAX, EBX, ECX, and EBX. And based on those program value, going to do the task that you are requesting for. Here, EAX is 3 and EBX is 2. It means that it's going to be a read call. So read something from the character array, and it's gonna put it in the location specified by the ECX register. And now ECX register has the address of label character array. So it reads the data and it put it there. So in here we define like EDX as 30 character. It means that the maximum that you could have is 30, but it could be less than that. Once you press enter, it means that that's end of the string, and the number of string variables that we could have could be less than 30. As soon as the system sees 0xA, it's going to terminate the data transfer to the memory. So you just execute this one and then return. When you return, where it goes back, you go back to the next line in here. In next line, we have print char, right? So what we do in here, is again the same thing. We define this one as global function. And again, this one is the external variable that has been defined somewhere else, and we use it in here. And we program our registers, the 4 registers that we know. We call the system to write, and the system is going to take a look at this and take a look at this, the memory that's specified by character array, and start printing those string from the character array until it reaches to the terminator character 0xa. So once it does that, it returns to our main function in here. And then we done. Okay, now let's take a look at the makefile. I guess you guys are right now very skilled in writing makefile. So this one is a simple one. So we have 2 ASM file and we have one main.c file. So what we do first, we produce the object files for this. And once we have the object file for all these source files, we come here and link them together. So as you can see here, the architecture of the makefile is kind of top to bottom. It's kind of in the reverse order as the shell script work, right? So it takes those object files, link them together, and produce the outputs here, main.out, where you can run it. I just added in here, commented here, the shell script, structure that we had before. This is not going to be randomized. These are comments. These are commented out just to let you know that you want to write the shell script for it. It's going to be like this, just to give you a sense of comparison here, how it's done. All right, so next, what we want to do, we just say make, since make create the binary before and no change has been done on this source file, then it says that your binary executable is up to date and no need for compile. So what is our binary file? Is main.out. So let's run that. So it's a simple program. It reads some character, like this, and you say enter. It reads it, put it in the memory, and it's printed out. As simple as this. So far, any question about this? You're probably going to have one similar question in the final exam.
Hey, Professor, I got a quick question for you.
Sure.
So do you need to have a pointer on that char array?
Yes.
Okay.
So this is our pointer. And if you remember in assembly, we normally use label, right, to basically point to a memory location. Always our label that we define, like in .bss section, are our pointer to memory, right? So that's the reason we need it, in here, we needed to define that as a pointer. It's a label to, in assembly, we call it label, memory label. In C, we call it a pointer. And okay. Yeah, so the way that we define it is like this. We define it in main to tell the other function in other files that this basically pointer has been defined somewhere else. We add a keyword extern. It means that this is basically a pointer that has been defined in some of the files. You tell the compiler, go and see where it was. So if we basically remove this extern, then the compiler is not going to be happy about that. Okay, any other question? Perfect. So now what we want to do is we're going to go to the lab. We are having some very interesting question in the lab, and I think you guys will like that. So let's come back to lab 12. This is a very interesting lab. So in this lab, you have basically 2 tasks. Where in first task, you are going to program some mathematical expression, some mathematical function within a C program using a C function as well as an assembly function. And then you're going to compare in terms of execution time, see which one is more efficient. Is it your assembly code that's written for that function is efficient, the processing time is less, or is it the function that you have implemented using the C program? All right, so here is the function. Okay, so I have f of x and y, where we define that as a division of x over 2 to the power of y. So we're gonna write a C code, right? We are going to have a C code in here. Where in this C code, we are going to implement two functions to calculate this f, x, and y. One function is going to be in C, f of C, and the other function is going to be f of ASM. So when they return, the value is going to be in the main function. So they calculate this value, then it's returned the value to the main function, and the main function we print out the results. One of the things that we would do in here, we compute the processing time for each of these functions. So let me see in here. Okay, so let's understand the problem, what we want to do. We want to compute this function once using a C implementation, other time using an assembly implementation. What we want to do, we want to compute the processing time for these two functions, see which one is more efficient. We define efficiency as a processing time, right? Because we are using the same resources, same hardware, same platform. When the function finished quicker, we understand that we kind of conclude that it is more efficient than the other one, which takes a bit more time. So how do we do this? Here's the implementation in C. So before we basically call the function, we start the clock. So clock T is a function that is going to start the time for you. That's the clock function in C. That's the begin. It's going to assign to the variable begin a time. Then you call your function in between in here. You call your function, and then your function is finished, and then you go to the next line. As soon as it's finished, then again you call the clock function. You register that value, you give that value to the variable end, and then what you need to do now, you basically subtract the end from the beginning, in here, end from beginning, to obtain the time taken to calculate this function. We give it the type of double to convert that, and then we divide it by the clock per second to get the time taken to calculate this function. So this is also a variable that is related to the system. It depends on your system clock rate. So, and that value is defined in time.h header file that you are going to include in your C function. We explain in here that you need the time.h in order to basically use the clock function. So once we call the assembly function to run this, and then we compute the time spent, and the other time we call a C function to calculate that, and then register the time taken, and then we print out the result and see which one is more efficient. Okay, so this is what we want to do in the first part of this lab. How we can implement that? Okay, so before going to take a look at the source code for this, just want to ask you guys that if you know how to implement this function in assembly. Anyone have some ideas of how we can implement x divided by 2 to the power y? I've explained this one before, you might have forgotten that. Can you think about the solution to do this very efficiently? Okay, so assume that you have some number, right, like this, 0, 0, 0, 1, right? And this number represents number 8, right? So let's do some shifting. Let's do some shifting to the right. So if we call this one x. Let's call this one x. So now x is 8. If we shift it once, what happened? If we shift it once, shift, that's the shift, arithmetic shift right for 1, then what you get is this, 0, 1, 1, 0, 0, right? Now it is 4. So it means that after 1 shift, we get 4. After 2 shifts, we get 0, 0, 1, 0, 2. After 3 shifts, we get 0, 0, 0, 1, right? And the value is going to be 1. So what is happening in here is this. So you have x 8. When you have 1 shift, basically you divide it by 2 to the power 1 for the first one, and you get 4. So it is going to be the value of f and x, y. Then when you have 2 shifts, you basically divide it by 8 divided by 2 to the power 2, you get 2. And when you have 3 shifts, you divide it by 8 by 2 to the power 3, you get 1. Okay, so basically then f of x, y is equal x divided by 2 to the power y, right? So what you need to do, basically, you need to put your number in EAX register, and then your Y number in a kind of like EBX register, and then you use a kind of shift right, for example, EAX as much as BL. We are assuming that we are not going to shift it more than 256, right? Because BL is 8 bits, and the value that it can shows is represented from 0 to 256. And since our register EAX is only 32 bits, we are not going to have a value more than that. So you see that this form of a function is in C looks kind of complex, but in assembly is just shifting to the right register, right? So that's very simple. So let's take a look at this and see how we can implement that. So in C, we can implement that using power function, POW. So we go first to task 1, see what we have in there. Okay. So first we take a look at our main C function. Okay, as is the talk at the beginning of this lab, so we need 2 header files in here. STDIO is just for the standard input and output. We need the map.h header file for the power function in C, and we need a header file of time to use the clock function. Okay, let's see how we do this. So we define this one as integer ASM function. It means that we are going to have an ASM function somewhere in our program. And normally, since the ASM is going to be implemented in different files, we should add extend, but as I explained for the function, the extend is the default, so you don't need to put it there. Okay, next we come in here and define some variable. We define f underscore c, f underscore sm. So these are the value of the function that value of the return of your function. And x and y are your input. Then the time for the c function and the time for the ASM function are defined as doubling here. And here we simply read these 2 numbers from the input and assign it to integer x and y. And then we are going to basically call our assembly function in between of these 2 clock functions. So you begin the clock, we compute the function, we record the end time for the function, we subtract the end and beginning to obtain the time taken by ASM. As simple as that. And then for the C, same thing, we begin the clock, we call the power function fc x over power of 2 and y, we end it, we calculate the time taken by the C function, and then here we print out the result in C. So we use the printf function saying that, okay, the value of the function returned by C is this, the time taken by the function C is this, and we say the value calculated by the function ASM is this. We just want to check whether we take similar values, and we print out the time taken by the assembly function. Okay, so one thing that you might be interested to see is our basically assembly function. You want to see how we implement our assembly function. As you can see here, this is simple. So it's just the .text. You start writing your code. Since ASM function has been defined as an extern in the C file, we define it as global in here, meaning that this is a global value that has been defined somewhere else, and I start implementing that. So these are normally the prototype that we use. We push the base pointer of the stack frame, we save it on the stack, and then we create a new base pointer for this function, right? And then here are the interesting point, right? So we are using two top elements from the stack. So we use those, we put in the EAX register, we put the other one. This is our X, and this is our basically Y, which is right now is in ECX. We said that since the value of it cannot be more than 256, therefore it can be represented using 8 bits. That's the reason when we do the arithmetic shift, we use the value of CL because we cannot have more than 256. And then we shift the value of X as much as 2 to the power Y, represented by this CL. So once we do that, then the value of the function automatically going to be in EAX. And EAX, if you listen to the lecture, you had some C calling convention. So always the return value of the function are going to be available in EAX, and C functions knows it. So when it calls the function to get the return value, it take a look at EAX register and understand that when I'm calling this function, right? So when C calls ESM underscore function, right? It gave it like two parameters, X and Y. So these X and Y are in here, right? And if you guys watch the lecture video, you know that once C pass the argument to a function, those arguments are going to be stored in the stack before entering the function. So X and Y are going to be stored in the stack when the program sees these two, and then it entered to the stack, so the return address is going to be added on top, and that those values are now going to be available for this ASM function. So there is a one-to-one relation. So then when I go to implement my ASM function, and I know that I have to work with two variables, and these two variables in C pass through the function argument, I know that these values are going to be in the stacks, where one element before the return address, right? So it's EBP plus 8. And since I have push EBP in here, it's going to be 2 elements. Take a look at these slides. So there are not much material available online. So don't search anywhere. I guess you can't find it. Even if you find it's going to be expressed in a complicated way, you will not be able to understand it. Just rely on this and try to compile the information here. So it said that interfacing assembly with C, right? So why interfacing? I'm not going to go through the lectures because it takes time. So I'm going to go to the C calling convention, right? C calling convention is in here. So since you are going to basically intervene or integrate or combine two different programs, you need to have a common language, right? If someone comes from country X and someone comes from the other country like Y, and you know they want to communicate, they need to find a common language, right? So if they don't have a common language, they are not able to communicate. So in here we have C and we have assembly, right? If you want to integrate these together, you know, have some C function in assembly, have some assembly function in C, you need to understand the language of the compiler, right? So compiler, when it compiles data into machine code, basically the intermediate step is the assembly one. So you need to understand how the compiler is acting in that way, right? So it's explained in here. So assume that you have a simple function of sum, and you want to call that function. So what happened below in assembly code, because it has to be converted in lower level language after the compile, right? So if you take a look at this compilation, we actually generated the assembly file for this simple C function in here. So if you're wondering what these are the assembly representation of your C function. So what happened when you call this C function, the system, what it does before calling the sum, it's going to push all those arguments into the stack. You see that? So this one goes to the stack. So this is where stack in here. Then 10 goes in here, 8 goes in there, 4 goes there, 2 goes after. And then when you go to the sum, then the return address is going to be there. And then you are here right now. So your stack pointer kind of pointing in this location. And then you go to the call, the sum function, which is in here. Once you go to the sum function, what you do, you save this base pointer for the stack, for the previous stack frame. You save that EBP in here. Now your return address in here. So the first element is basically 8 byte space away, because this is 4 byte, this is 4 byte. If you want to access these two, you have to move as much as 8 byte. So if you do that, you move that, it's gonna, this EDX value is going to have the value of 2. Then if you take the other one, move 4 elements down, you're gonna take the value of 4 in here. When you add them together, it's going to go to EDX register, for example, 2 and 4 going to be 6. Now you add the next element. Next element, where is that? So it's going to be this one, 8, so it's 16 byte lower, right? You put it in EAX, then you add 6 with that, then EDX this time is going to have, for example, value 14. Then you go take the next element, which is 4 byte down, so it's that 20 EBP plus 20, and then you add that, you pop EBP from here, and then you return in here, right? So the value that you are getting basically is EAX, is stored in EAX. So this is the convention that I'm talking about. So when you call the function, the arguments are going to store in the stack. When you come back from the function, the return value is assumed to be stored in EAX. So this is a common language. You want to just tie an assembly function in here. So this is the way that the compiler is interpreting that. So you need to talk the language of the compiler. So there is no other way. So you need to understand the language, right? If someone comes to this country, right, they have to talk English. If they talk like Mandarin, if they talk, for example, Malaysian or Persian, no one can understand them. We have to talk English once we're in the US, right? In order to communicate with other people. In here, we need to talk in the language of the compiler. And this is the language that the compiler interprets the information. Okay, I guess we have all these explained in here in a clear way. So you guys, return address, push EBP, it says what is A, B, and C, and D. The return value is stored in EAX. So these are the calling convention that you guys need to understand, right? So the parameters are pushed on the stack on the reverse order. Do you remember 10, 8, 4, 10 goes first, right? So reverse order means that whenever you have the argument like this is your first element, but the first element that goes into the stack is your last element, 10, right? Referring to the previous example. Then the caller removes the parameters from the stack. So what does that mean? It means that in here, basically when you return to that, these values in the stack gonna be removed by the caller in here. So this is the convention. If you go back one more in here, you see that this is the caller, right? We had 4 elements in the stack, and we now add ESP plus 16. It means that we point the ESP pointer in here. Once ESP point in here, we basically free this much space available for the next function. We just need to get rid of this. We don't want to accumulate garbage into a stack once we're done with the function, right? So these are the calling convention. So the return is going to be in the EAX register. So you assume that these values are preserved. So when you're working with function, so this value you have to assume that these are preserved, and there are some values in them that they're going to be used. So if you want to work with this register, make sure to push them on the stack and pop them back after you're done with the function. Okay, so if you want to see more calling convention, goes to this tooling, but these are the main thing that we are using here in our implementation, the main one. So you need to understand how the argument goes into functions and how the return value is expected in C. All right, this explains that, right? So our X and Y are pushed into the stack now. Let me see if I can write in here. Yeah. Okay, so as I explained, so before we come to this function, right? So once we are in here, and these are our arguments, right? These two elements, X and Y, are pushed into the stack in the reverse order. So Y is going to be there, X is going to be there. Now we call ASM function, then the return address is going to be on top. So once we reach there, then we push EBP on top of that, and then we create a new stack frame. So right now, ESP, we point the ESP pointer to EBP. You guys, we have explained this one the last two lecture, I think. Then this is the way that we do the computation. So let me just draw the stack for this because you guys need to understand this in order to implement a similar thing in the future. Let me see if I can have one board in here. Right. Let's rotate. Okay, that's nice. So we said function is a function X and Y, right? Let's write it in here. Is function X and Y. So we said as soon as we form this function and we want to call this function, right? These two are going to be stored, the value in the stack. So we are assuming that these two are in the stack, so X and Y. And so once we call the function, the return address is going to be stored in here, right? So now we are in the function. So these things has happened. So we are, you know that Y is in here, X in here. And then next, then we insert to the function, we push EBP. So the stack, this is the previous base pointer for the previous stack frame. So we save it in here so that once we are done with this, we pop that value up to send the base pointer to its previous value. Now we are here. And what we want to do, we want to compute this function X divided by 2 to the power Y. So we said that to do this, we put X in EAX register, right? And then the arithmetic shift right, then EAX as much as the other argument, Y, where our Y right now, so let's explain this first. So we first take EBP plus 8. So right now, EBP basically point in this here. Then we say EBP plus 8 is going to point to X. So EBP plus 8 is going to take the value of X, put it in EAX register. Now we say EBP plus 12, now it's pointing to the Y, put it in ECX register. Since the value of it, we said that we cannot, so we have to choose the X and Y where Y is not more than 256. Therefore, we just take the CL value of the ECX register. You guys know that, right? ECX is a big register where you have your AX portion in here, right? Then, sorry, CX portion in here, and then you have CL portion here, CH portion in here, right? So since our value is less than 256, therefore we take this value and put it in ECX register. The other thing that we do the shift right. We said, right? We do shift right EAX as much as CL. And what we do, we implement this using this simple calculation. And now what we have, we said that, okay, once we return from the function, expect to see the return value in EX. So and here automatically it happened for us. So the value that we shift after this is going to be stored in EAX register. So once we come back, C will take the value of EAX as a return function. As the return value of the function is if our function is not void, right? So therefore, coming back in here, it assigned that value to f of ASM. So now we have f of ASM, then we compute the end time, we subtract these two, we compute this value, and then we print it out down here. So here the implementation is implementation for C. For C is much easier, just x divided by power of 2 and y. You register the value of the clock at the end. You compute time of f of C, and then you print it out those values in here. Okay, any question? So I recommend you guys don't take a look at the solution. So I'm going to be posting this on the website, on the course canvas page. So before looking at the solution, try to implement this by yourself. And once you're stuck, then you can come back and take a look at the solution. But these are not complicated, you know, functions are very easy. It's just you need to do it yourself first before taking a look at the solution. This way you kind of make yourself more comfortable writing this kind of code. Okay, again, we have a make file here. We define the options in here, and then we have how many files? We have 2 files. We create the object file for it, object file for this one, and then what we do, we link them together in here. Minus LM is the switch that's needed because of the header file in C. I explained this one in the lab, and I gave this code, this GCC for compilation in the lab to tell you how to basically link them together. The only thing that you need to add for this one is minus LMX. This one has been given in the lab instruction. So you have your function in here, and then you say make, it says this up to date. So the binary file is main.out. You just say that. So we are going to have value 8 for X, value 2 for the Y. So it means it says that the value computed by C is 2. The value computed by assembly is 2, so the value are equal. The time taken by C is this much, 00017. The time taken by the assembly is this much, it's 503, right? So it's much, much less than that. So if you divide that value with this, you are going to see that it is 6 times faster. Any question? Perfect. Next one is calling C function within an assembly program. So in the previous one, you had the main C file, and our file was C, right? And then, like this up here. Okay, that's right. So we had C file, and then we called some ASM function, right? Now it's reversed. We have some ASM function. We want to call some C file in here, in this task. So write an assembly program like this that reads an integer from the input by calling a C scan function, and compute the following expression using C function. So not only you read the values using a C function, but also you compute this value using C function. So in here, what I wanted you guys to do is to understand the language of communication between the assembly and C. So know where the arguments are going to be saved for the function to be used. So for that, you need to know the calling convention of C. And then, so once you calculate this, you are going to print the result. And after that, once you write your function, you need to write a make file. Once you write your make file, you just need to run it and see if it works. Okay, I'm not going to go through that. Just want to show you how the function, only thing you need to know is the language of communication to implement this. Okay, so where we are here? So we have task 2. Go to task 2. Okay, in task 2, I have my ASM file. So this is my ASM file. Very simple one. So I have defined this one as extern, right? Power, cubic, print, and read. So these are functions. Then global main, I start writing my assembly code as usual, right? Then I call read integer. So this read in is implemented in C. Where it is in here. if I put all those functions in my tools.c. So I didn't create like one file for each of these functions. So all of them are available in C in this file. So this is the file. So the read function, as you can see, so this is a read function. There are two arguments for that. So we call the scanf from C. We read those two values. We know that they are integer defined by this %b, and they're going to be stored in an address specified by pointer A and B. Okay, so once you basically come back, so you know that these values are stored in the stack, where in the stack the addresses are kind of pointing to those values into the memory. Coming back to the function, so we read those, we put it in the stacks, we call the cubic function, and we compute the value here. So that's the cubic function. It's a very simple one. We multiply A by itself 3 times, plus 1, and return that value. Once the value is returned, we know that it is in EAX register, right? So it is in EAX register. We know that when we call in the function, in our function, we work with the stack. That's the reason before we go and print that out, we push that value into the stack. So the resulting is in EAX, we push it into the stack so that when we go to print it, we take it out from the stack. So now we call the print, we come back to my tools.ca. So here is the print function. We know that we basically put that in the stack. So once the print function is going to print something out, and it knows that this is an argument to a function, it knows that that value is basically stored in the stack. And it's going to add the return address, push the EBP on top of it, and then the print function is going to take the value A from that location in the stack and print it out. So the next one is to removing the value of the power from the stack, from the cubic, and then go to the power function. Compute the power, push it on the stack, then call the print it out, now clean up the stack, and then exit from the program. Again, please go ahead and implement this by yourself before taking a look at the solution. So I'm going to post the solution today on the course Canvas page. So do the implementation and take a look at the solution, see how it can be done. So Makefile is again going to be available in the solution, so you can take a look at Makefile. In here you have a new file like mytools.ca, so we generate the object file for it. And since we have two source files, we link them together using GCC here. And then your output file in here is main. So if say make, so it is up to date. It's not up to date yet. Okay. Yeah, so we have changed one of the files. That's the reason the binary has been generated for us. So these are the value. And so this is the cubic, and this is the other function, the power function.